Welcome to my second video on how to build a Z80 computer on a breadboard. This is a continuation of my first video, which has the same title but was subtitled but we're afraid to ask. The difference between this computer and the other one is that this has been built on a much larger breadboard, so everything would fit on one board. It also uses a 74 HCT 138 decoder multiplexer chip in the I/O decoding circuit, so that circuit would be more flexible. You can support up to 8 different drives, or 8 devices rather. And it also has the main thing about it. It has the compact flash adapter with a card inside, so it has permanent storage capability. Now, I will start this video with a demo, which is the usual thing to do. And then in the second part, I will explain how I did it. There is a reset switch here, which I will activate in a minute. But if you turn your attention over to the compact disc, you'll see that there are 3 LEDs, green. The middle one is yellow, but it's off, so you can't see the yellow color. And then there's a red one. The green one is power. The red one tells you that if it's on, the card isn't inside the adapter. The yellow one flashes actually when it is accessed. Okay, so now I'm going to start it. Put your eyes on this middle LED and you'll see it flash. There it is. It has just read in 512 bytes of data from this card. And now what it's doing is, since it copied it to RAM after it read it, I am verifying that data by echoing each byte on the LEDs here, and I put a delay in between each display so I could read off the bytes. When it's done reading the 20 and echoing them back, then I will turn my attention over to the terminal, and you will see the program executing after a jump instruction is executed that will transfer control over to the first instruction of that program. In the first version, I used ROM exclusively. There it is, the venerable Z80 demo. This one is using RAM. Please enter your name or X to exit. I will type in a name. Type my name, it echoed it, and it looped back to accept another name. If you hit X and enter, you get the "Have a nice day" message as the program is ended. And that's it. In the second part of the video, I'll show you just how I did it. Now, to explain the 74 HCT 138 8-line decoder multiplexer chip. This chip takes 3 input signals and produces a single output signal, depending on the pins A, B, and C. To activate the chip, we need G1 to be high and G2 to be low, as you can see in the rectangle I outlined in red, right up here. Okay, but G2 itself, if you see below, is G2A plus G2B, which means those 2 signals are ORed together to generate a low signal. Therefore, both G2A and G2B must both be low. That's the way OR operations work. So, once you get that set up, whatever pins are hooked up to that give you those H and L values. We know that one of these rows, from the 3rd row down to the bottom, will be active, and only one at one time. So if we want to use Y6, which I did in my computer, I want that low signal to be on that pin. I need ABC to be HHL, as you see in this oval right here. So therefore C must be H, B must be H, and A must be low. Okay. Now, which pins to use in the Z80 to accomplish this? We know that the IO request signal will be low for this operation of input-output. And the other ones wasn't really sure. But fortunately, Spencer Owen, who has produced an RC 2014 computer, which I have built, a couple of them. This is the compact flash board coming with one of them. And you can see there's a chip there under that hex 10. That's a 138. And they actually described it here, and the documentation shows just exactly how they hooked it up. So I did the same thing. I followed their lead, and if you look at it, you see that A0, A1, A2 on the top are hooked up to A3, A4, A5. And you can see below, they hooked up, it's a little hard to see, but they hooked up M1 to G1. If you follow the lines in the schematic, G2B is hooked up to iRequest, and G2A is hooked up to address pin 6. So coming back to the chart, that means that I did the same thing. So that means that G2A, A6, will be 0 in the port address, and CBA, which is A5, A4, A3, will be 110. That means that in my port address and the out instructions that I use to communicate with the compact flash adapter, the high order 4 bits would be 3, the value of 3. Okay, then what remains to be done is you would then take the Y6, in my case pin 9, from the 138 and connect it to the chip select pin on the adapter. In the next segment, we'll get into how I connected the compact flash adapter to the Z80 and how I programmed it. See you then. Before I get into the nitty-gritties and the meat of this video, I would like to point out a few things about the adapter itself. If you look at this diagram, which is in the Wikipedia article, which Matt Cook has included a link to in his article, you can see a nice diagram of the adapter pins. If you look at it closely, you will see in the middle top part of the diagram a protruding part of the adapter itself. If you take your adapter and you look at it closely, you'll see that protruding part. If you orient your adapter the same way the diagram is, you'll know where pin 1 is. It's in the upper left part of the diagram. Pin 1 is on the top, as are all the odd pins. The even pins are on the bottom. It's as simple as that. Now let's move on to the second point. To copy a file onto the card, you need to actually just drag the file in, and when you do, let's see, I had done this earlier, you'll see this file, iostir1200.pin, which is actually the program that I used in my demo. To look at the code, you would go to, say, Notepad++, and then you would look at the listing, and you can see that the first few bytes of this code would be 210 Fox 81. Then you could run a hex editor program like HXD, run it as an administrator so you could access physically the contents of the drive, go to the tools menu, and then drop down to open disk, that sub-item. Now you see that there are two parts here, logical disks and physical disks. You need to look at the physical disks. When you read from this card, you will be loading in this part, not the logical. If you look at the logical part first, you could see the contents is a boot sector. The first byte is EB, which is a jump instruction, and the last byte here is 55AA, which includes that boot sector. But if you look at the other one, let's look at that one. First, tools, open. Let's go to the physical one. You see the contents are not the same, but it is still sector 0. So that part I really didn't quite get when I first started, but figured it out later. So now let's look at the code itself. So if you do a search and you look for this 21.0.Fox81, you will find that it exists at offset 43800, which is sector 540. Then what you would do, you would take a calculator and you would type in that address of 540 in decimal. Let's clear this first. 540. And you can see the hex value would be 21C, 21 Charlie. That is the sector address that you would put into your code. You would place it, I will show you where, right here. So instead of a 59 value hex loaded into CFBA0, you would include the value of 1 Charlie. And then the 2 part you would put in the next register, CFLBA1, and I already had a 2 here for the other one that I used. This is the value that I actually used in my demo. As you can see, there was a question of how to enter the address other than 0 into these LBA registers, and it turns out it looks like it's entered as a big endian number. If it was a little endian, I believe the O2 would be in CFLBA0, and the other value, whatever it is, would be in the CFLBA1. Okay, that's all I really want to say about the card, except possibly one more thing. This card, this adapter actually, is a 40-pin adapter. There are other adapters that have more pins in them, and that could be confusing when you look at their diagram. So it would be wise just to say with the same one that he used, which is the 40-pin adapter. Next, we'll get into a little more detail about how I actually connected the compact flash adapter to my Z80 computer. Now that I have explained how I set up the 74HCT138 decoder multiplexer IC, I will now move on to describe how I interfaced with the compact flash card adapter. When I was searching for such an interface, I came across this article written by an electrical engineer named Matt Cook, who posted this on the internet on July 6, 2015. In the article, he describes just about everything you need to know, and he does a very good job of it. It's fairly clear, except for just a couple of points which I hope to clarify. He has in it a link to a Wikipedia article as well. He supplied another link down below to his Z80 project repository on GitHub, so you can download his code, and you can use it with just a few minor changes, which I have done. Okay, now to get on with the problem I encountered, the main problem I encountered was understanding this paragraph. So I'm going to read it. He said in the middle of this paragraph, I mapped the CF card to IO address hex 20 to hex 3F, only needing the first 8 addresses for access to all of the CF card registers. So I didn't really understand what he meant exactly when I first read it, but later on I realized that he used the 3 low order bits, meaning the first 8 addresses of his port, to select which register down here you're talking to when you issue an out instruction in his code. So, to understand it more fully, I will show you a diagram I wrote. I created this diagram, this table, where I show you 8 different port addresses, 1 for each register you need to access on the card. The most important thing to realize here is what the Z80 does when it executes an out instruction. As you can see, I wrote the Z80 out instruction will load address pins A0 to A7. That's very important. First, to use the out instruction, you would load a register A with some data, and then you issue the out instruction with a port number. Let's say you could use a register, but that's a different format. But if you use the number, this would be the way you do it: out, port number, comma, and the register A. When the Z80 executes the out instruction, it will put on the data bus the contents of register A, and then it will use the port number to set the address pins A0 to A7. So if you use a port as I have put on the first line of 00110000, then when the Z80 executes the out instruction, A7 will be low, A6 will be set low, A5 will be high, A4 will be high, and A3 to A0 will be 0. As you can see, I use the 3 value in the high order 4 bits of the port number because, as you saw in my last section of this video, I am using 3, and 0011 is 3 in hex. 0011 is the value I use to activate the 74HCT138 decoder multiplexer chip on my Z80 board. And the low order part then will be used to access which register on the flash adapter I'll be outputting data to. Now, to hook that up, let's go back to the code. This is actually his GitHub code you're looking at right now. And he states, the addresses that the CF card resides in I/O space change to suit hardware. And you can see he has a sum of CF base plus a number from 0 to 7 used to select one of these registers on the card. So the game is what to assign to CF base to make this work. If you do what he did, you won't need much as far as the actual address to address the register, because you just use the value 0 to 7. I don't know what he used for his CF base because I don't know how he designed his I/O decoding circuit, but I know I need a 3 to start with, and the rest of it, if I use A0, A1, A2, I could just use this formula, CF base plus the number as is. So if you look at my code, which is here, you can see I equated the CF base to 30 hex. That takes care of the multiplexer chip. Next part, I add the numbers 0 to 7 to that ZF base, so that when my code assembles, and I'll go to the listing of it, see if I can find it. Here it is. Going down to a typical out instruction, say CF stat in this case, you can see in the object code that the assembler generated 37 in the low order part of the instruction, meaning the 3 will handle the decoder multiplexer chip, and the 7 will select the CF stat register on the card because it has been equated to CF base plus 7. That's where the 37 comes from. Okay, now here's the problem. When I first looked at it, not understanding exactly what he did, let's look back at it. Go back, back, back. Okay, I'm trying to find, here it is. Okay, now looking at his code, you can see if you want to use this formula, you really need to use A0, A1, A2. Because let's say you wanted to use a different 3 registers, say A1, A2, A3, you would have to shift over or multiply this value by 2. You couldn't just add 1 to 7 to your base. You'd have to add, say, instead of 1, 2, instead of 2, you'd have to add 4, instead of 3, you'd have to add 6, and so on. And what if, the worst case, What if you wanted to use registers A7, A3, A4, any arbitrary 3 registers? Well, you couldn't use this formula at all. You couldn't really probably make one up. You'd probably have to hard code in each out instruction, such as this one. You'd have to figure out what value to use. Each one would be different. Okay, so that covers that area. Now the next area I want to talk about is the LBA. So let's go back to the article. In the article, he discusses the logical block address versus the sector, head, and cylinder addressing scheme. You need to set that particular bit on the card so that it will use the LBA, because the device itself is a solid state device. It doesn't have cylinders in it, doesn't have heads in it. Okay, so in order to do that, if you look at his code, in this area, he has 4 out instructions, starting with this one, which is outputting from register A a value of 0 to CFLB A0. He has one for A1, he has one for A2, and he has one for A3. What he put in the first 3 ports is the action of the data, rather, is 0, because he's using 0 sector address. So it's a good way to start, as he recommended, to try to set this up using the first sector on the disk so you can see if it actually works. Then you can put later on, copy a file to your card, find out what sector that file is in and locate it in, and then you can then change these addresses here to suit that sector. So now, another thing about this is the E0 load into CFLBA3, where that comes from. He states that the high order 3 bits, that is LBA 24, 27 plus drive 0 selected over here, he states that you need the high order 3 bits to be high. Actually, I looked into a little further and I found this document showing you that on the card you have a cylinder register in 2 parts, because there's a high and low order, 8 bits each, and you have a drive head register. And in the drive head register, you can see here in this part, you can see that bit 7 is hard-coded as a 1. This bit is set to 1 in the description. Bit 6 is the LBA, so it's really only 1 bit setting the LBA. This is the confusing part to me, because if you look at the code inside the function description, it says LBA 27, LBA 24, drive head register bits H33, HS0, HS0. So when you look at his document, he does mention. Let's go back to his document. Okay, find it sooner or later. Here it is. He states in his comment that LBA bits 24 to 27, read-write LBA mode. Okay, so it actually, now going back, you see the 2427 number. If you go back to that document I found, let's see if I can find it. Right, that's where this comes from, LBA to 24 to 27. So it looks like maybe 4 bits are involved in that here, but the 4 bits are shown down here. So it looks like the E0 comes from 1, 1 for the LBA bit, 1, and then 0 for the rest of it. So that's how you would get E0. But so that's slightly confusing, because inside this 1 bit you have all these 4 things, these 4 registers are set. So as you can see, bottom line is, he's correct. You just need to load E0 in that particular register, as he has done in his code down below. Just load an E0 into CFLBA3 and it'll work fine. Okay, now let's move on to the actual hardware connections. He has a very nice diagram of the card, and I have described already A0, A1, A2. These 3 pins are what you would hook up the Z80's 3 pins you're using, let's say A1, A0, A1, A2, which I used, corresponding to A0, A1, A2 on the card. Those set, and I also described my 138, so I had hooked up the output of the 138 into the IOCS chip select 1 pin, pin 37 on the card. He didn't mention the other one, but probably not to confuse you, but on the other side of the interface card on the adapter, there is a pin 38. That is actually IOCS 0, which he hooked up through a 1K pull-up resistor to a 5-volt power source. So those 4 pins are explained. The pin on the bottom of the IOCS 1 is an activity pin. So if you use an adapter, such as I use, such as this one, then you don't need to set that pin at all. If you don't use the adapter and you hook up directly to the card physically, maybe you solder it up, then you probably need to use something like IO request active and chip select active, something like that, to connect to pin 39. So now, and then you of course have to supply your own LED to show if the card is if the adapter is active. The rest of the pins are fairly straightforward. What you would do is, starting from the top, MR must be master reset. So you would hook up pin 26, the reset pin on the Z80 processor, to that pin 1 on the card. You would connect the 8 data pins D0 through D7 on your data bus to the corresponding data pins on the card. You would connect the write pin and the read pin from the Z80, which would be 21, 22 respectively, to the card. And then you would need power hooked up to one of these pins. Let's see, did he actually show the power here? Yes, he did. It's pin 20. 19 on the other side is hooked up to ground. On the other side, on the same side as the power pin, you have pin 2, 22, 24, 26, 30, and 40, all connected to this triangle, which represents the ground. And what's remaining is any pin he ended in an X in his diagram. Well, these pins don't have to be connected at all. That completes the setup, the connections, and that completes the whole description of how to use this adapter with the Z80 computer. I would like to point out a few things that I discovered while creating this computer. There are dip switches that have pins in it that are too short. I know this is unrelated to the topic, I just want to mention, and if you look at Amazon, you'll see a lot of people have bought these dip switches and they really don't work well on the breadboard. I use them at first. They are colored red with white switches on the main body, and they just don't work well. So if you look hard enough, you can find one that really works. So I replaced those other ones with the ones that do stay on the board. You could also use a resistor array and an array of LEDs, which they take up less room on the board, and they're kind of neat. But I stayed with the LEDs, the physical ones that is, because I wanted to have different colors on the light so you can easily see the value in hex when it's displayed. So I used 2 different colors, one for the high order and one for the low order. So that's very important, but I thought I'd mention that. That completes this description of how I set up the Z80 with a compact flash card. If you have any questions or comments, please feel free to send me them, and I will do my best to answer.